Okay, so thanks for coming. So this is the last lecture that I'm going to give on closed string field theory. So by the end of this lecture, I'm hoping that we will start to see the monster come into view, but I don't think I will quite have enough time to pull together all the ingredients that I might have liked to, but I think we will have discussed somehow the non-trivial concepts. Okay, so last time we were talking about off-shell amplitudes from Feynman diagrams. Okay. So the idea is that we want to, instead of considering a generic kind of uninteresting section of p hat gn and defining an off-shell amplitude in that way, we want to construct an off-shell amplitude by computing Feynman diagrams. Of course, this will be closely related to actually the construction of a space-time field theory action for the closed string. So in order to build Feynman diagrams, we need two ingredients. We need a propagator and a cubic vertex. So normally these would be given to us by the action, but we don't know the action yet. So instead, I just want to motivate the form of this propagator and this cubic vertex, and then use that to construct the action. So the propagator is a map from H into H. It's basically a linear operator acting on the state space, which is given by B0 plus over L0 plus B0 minus delta of L0 minus. Okay. And this can be expanded using the Schwinger parameterization into an integral from 0 to infinity, ds, integral from 0 to 2 pi d theta over 2 pi, and then e to the minus SL0 plus I theta L0 minus. Okay, so the plus and minus plus is B0 plus B0 bar, and minus is B0 minus B0 bar. So this object in here, this operator in here, which is being integrated, can be interpreted as attaching a tube of worldsheet to our state. So if our state is here, we paste a state coming in here, and then we attach this tube of length s and some twist angle theta. Okay, so this is this tube represents the free propagation of a closed string. So we also mentioned that you can also view this operator in the conformal frame of the disk that the propagator acts on. So if you start with a state represented by some vertex operator on the unit disk, okay, and you apply e to the minus SL0 plus plus I L0 I theta L0 minus. And this will still give you the unit disk. Okay. So this is unit disk, so this is 0 and this is 1. But the disk of the state will be shrunk and rotated. Okay, so be rotated by some angle and will be shrunk. And then this annulus in here is just this tube expressed in a different conformal frame. Okay, so that's reviewing the propagator. So now let's talk about the cubic vertex. So the cubic vertex will be a map, which we will write as V03, which takes 3 copies of the state space into 0 copies. So it's basically a coupling of 3 states. Okay. And we can identify this cubic vertex simply with the off-shell 3-point amplitude. So we can write V03 will be the same as the off-shell 3-point amplitude, which in itself is the same as a surface state with 3 punctures. Okay. A surface state on the sphere with 3 punctures. Okay, so there's some degeneracy of notation here. So I will use the state V to represent a vertex which appears in the action of closed string field theory. A is not a vertex of the action. It's the full off-shell amplitude, including contributions from propagators and Feynman diagrams. Okay? And sigma is just is the surface state. It's a surface state, and usually this surface state needs to be integrated with some B ghosts. But in this case, it's not integrated with B ghosts because the moduli space of the 3-punctured sphere is 0-dimensional. Okay.
So A is not part of the diagram which is not truncated on the external legs, while V is truncated.
You mean so A is not a Green's function. Is that what you're? V is a vertex in the action.
And A is a Green function.
No, A is the Green's function with the external legs dropped off.
Okay,
So it's really the amplitude, but it's off shell.
okay.
Okay, in general. Okay, and
This is true only because you have 0,3.
yes. So there's some degenerate. So it looks like I have copious proliferation of notations here, but I just wanted to emphasize that these, in general, will be 3 very distinct objects. But they happen to all be the same in the case of the cubic vertex. So by this equality, the cubic vertex acting on 3 states, phi 1, tensor phi 2, tensor phi 3, is given by this surface state, which in itself just computes a correlation function with the 3 vertex operators inserted on the sphere with some local coordinate map. Okay. So these local coordinate maps, F1, F2, and F3, are specified, so these coordinate maps are specified by a quote-unquote section of P hat 0, 3, okay? But the base manifold is just a single point because the moduli space is zero-dimensional. So really, okay, we're just choosing a point on a single fiber, okay, and this specifies our choice of conformal maps and defining this surface state, which in turn defines the cubic vertex, okay, which we will use to compute Feynman diagrams. So, okay, so one thing that, a condition that's imposed by definition okay, the cubic vertex should be symmetric. Under interchange of any of the two states that it's acting on. So that means that this vertex acting on phi 1, phi 2, phi 3 should be equal to, okay, we can switch the order of phi 2 and phi 1, or, okay, any of these permutations, and we should get the same object, okay. Okay, but this will not follow automatically from the expression that I wrote, okay. So, okay, this is a condition which, okay, is effectively a definition, okay. So, but we could fix up this this identification that I wrote here by just taking these conformal maps and just summing over all possible permutations where these maps act, okay, in different combinations on phi 1 and phi 2 and phi 3. Okay, so in total there would be 6 terms, okay, for the 6 permutations of phi 1 and phi 2 and phi 3. So we should write, 1 over 3 factorial times all the permutations of these correlators here, okay. But this kind of resolution is not typically considered ideal. And the reason is that effectively V03 is specified by 6 distinct sections of P hat 03, okay? And it's considered inconvenient to work, okay, so we can generalize what we said before to discuss off-shell amplitudes defined on linear combinations of sections, okay, there's no problem with that. Okay, but this is not considered ideal because then effectively you multiply the number of off-shell amplitudes you have to keep track of. So it's, in practice, you don't symmetrize these conformal maps, okay? Instead, you impose a condition okay, that the 6 sections of P hat 03 obtained by permutation are identical. Okay, so that means that you make a very special choice of section, okay, or a very special choice of these local coordinate maps in such a way that this vertex is identically symmetric without having to explicitly symmetrize, okay? Yes. So in this sense, I was just trying to motivate for you why. Okay. So that's why you see that the vertex is effectively has to be symmetric, right? Because it's always symmetrized automatically anyway. But since you don't want to proliferate the number of sections or off-shell amplitudes that you have to consider, it's just better to assume that you have symmetry off-shell from the beginning, okay? Well, it's more than Z3, it's a full permutation symmetry. Yes, okay, but such a conformal transformation will alter the maps F. So when you do a conformal transformation here, you have to change the map F, and you have to be sure that in the end you get the same thing. Okay? Yes. Yes. So there's a subspace of this section, which is symmetric, and we should choose our vertex from that subspace. Sorry, a subspace of this bundle, which is symmetric. So this is not proving anything. I'm just telling you what people do, and just the belief that if you choose something that's not symmetric, it's just going to make your life more difficult, okay? Because you just have to keep track of more things. Okay, so, okay. So with this, with this motivation, let's discuss some examples of cubic vertices. Okay, so so first example will be the SL2C vertex. Okay, so this is defined by formal maps F1, Xi1. Okay, now let me make sure that I write this down correctly. Xi1 over Xi1 plus 3, F2 Xi2 equals 3 minus Xi2 over 3 plus Xi2, and F3 of Xi3 equals Xi3 plus 3 over 2 Xi3. So this is an explicit choice of section of p hat 03, okay? So, so we can, so I've chosen these maps so that F1 at 0 equals 0, F2 at 0 equals 1, and F3 at 0 equals infinity. Okay, so you can you can draw, okay, so you can consider the z coordinate on the sphere, basically the complex plane representation of the Riemann sphere, and then you can see how these unit disks of your states, so here's Xi1, Xi2, Xi3. So how they map into the sphere, and then you find, okay, that since these are SL2C maps, they will map these regions into circles. Okay, and the circles look like this. This is 0. This is puncture at 1. It's a puncture at infinity. Okay, so F1 maps like that, maps here into here. F2 maps from here into here. And F3 maps. So, okay, so in particular, the local coordinate patches, just to emphasize that here the patch of the local coordinate patch of Xi3 is outside this big circle, and the coordinate patches of the other guys are inside these small circles. Okay. Okay, so this is a nice cubic vertex. It's going to be the basis of our calculations. Okay, so another example is the Witten vertex. Okay, Witten vertex. Okay, and this is given by these conformal maps. F1 of Xi1 equals e to the 2 pi I over 3. 1 plus I Xi1, 1 minus I Xi1 to the 2/3. F2 of Xi2 equals, okay, just again this factor. To the 2/3. Okay. So so these guys, okay, instead of mapping to 0, 1, and infinity, we have F1 of 0 maps to these this triplet of points. Okay. E to the 2 pi I over 3. F2 of 0 equals 1, F3 0 equals e to the minus 2 pi I over 3. And we can draw an analogous picture in this case. Okay. And now we have a puncture here at 1. We have a puncture here roughly at e to the 2 pi I over 3, and a puncture here at e to the minus 2 pi I over 3. And, okay, and we have our disks. Where, okay, so turns out that the image of the disks are these 3 wedges. So, so Xi1 maps into this wedge here. Xi2 maps into this wedge. Okay. And xi3 maps into this wedge. Okay. So unlike the SL2C vertex, the SL2C vertex, there was some surface left over. So there was some surface that was not contained in a local coordinate patch. The Witten vertex is special because there's no surface left on the sphere. Everything is covered. Okay. So in fact, if it's helpful, we can also transform this picture into a picture like that, although it's not standard. This is not the standard representation of the Witten vertex. But if you make an SL2C transformation to map these punctures into the canonical positions, you find that the analog of this picture for the Witten vertex looks kind of like this. Okay, so you still get these bubbles. So you have three bubbles, just like here, one bubble around the origin, one around 1, and one around infinity. Here you have a bubble around the origin, a bubble around 1, and also around infinity. But here we don't have this uncovered surface. So everything is totally fitting together. Yes? Uh-huh. Yeah, so this can be either of these vertices, or in fact any vertex can be modified by adding what is called stubs, which is basically just attaching. Yes. So this is the the somehow the most stubless version of this vertex. Okay, it's kind of a weird word, but so if you try to expand out the xi coordinate any more, then you will find that these circles, that this circle comes in too far, and these circles expand out too far, and they start to cover each other. So on the other hand, if you shrink by the xi by some factor less than 1, then they no longer touch here, and there's there's a connected region which separates all of the local coordinate patches. But I don't think we will need to worry about stubs, though that's actually an important concept, but unfortunately I can't say everything. But yeah, so this was the exercise. So I'm sure all of you are taking my exercises really seriously. So here's another one, in case you're bored. Okay. So exercise. Prove that SL2C and Witten vertices, Witten vertices, are completely symmetric. Okay. So in fact, if you are looking for vertices made up of SL2C maps, then imposing symmetry fixes these conformal maps uniquely. Okay. Up to, of course, a phase rotation of your disks, which you don't care about. Okay. But, okay, so this is a little exercise just to show that these things are symmetric. What? Well, Witten is obviously cyclically symmetric. If it's, it may also be obvious to you that it has full permutation symmetry, but I'm not.
The reflections about the x-axis values.
Yes, yes.
This gives rise to a different permutation.
Yeah, but you have to use global SL2C to prove this.
Yes. Yes. So, yes, so in fact, maybe it is obvious in that sense. I was actually thinking more of this vertex in that context. Yes, but okay. Yeah. And there's a little bit of an ingredient in there as well, but okay, so you can think about this as a little exercise. Yes. Yes. Okay. So, so there's a third vertex. Oh, wait. Okay. I wanted to make a further comment about Witten's vertex. Okay. So Witten's vertex is naturally related to the minimal area problem. So Barton Zwiebach, back in the early 90s or so, proposed a way to find a global section of PGN, okay, which gives the simplest possible closed string field theory in some sense, okay. This may be a little bit controversial, but it is a very nice global section. And it's basically defined by requiring that that you find a metric of minimal possible area on your Feynman diagram under the condition that closed curves around non-trivial cycles in this diagram have a length that's bounded from below by some number. So this prescription actually gives you a unique choice of closed bosonic string field theory. Okay, so that gives you a preferred section of PGN, a preferred global section of PGN, and a preferred choice of field variable. And this prescription, in fact, implies that the cubic vertex you need is this one, okay? But this one should also work, okay? And this one is actually easier to work with in practice, at least for present purposes. Okay, and there's another vertex which maybe is discussed in recent times, based on Pius and Musavian's attempt to find a global section of PGN using metrics of constant negative curvature. So it turns out that you can compute the cubic vertex using their prescription, and you find that these f1, f2, and f3 are given by modular lambda functions. And then, but the picture of the local coordinate patch looks rather similar to this one. Any questions? Okay, so you have several different possible choices of cubic vertex, and these different choices should be related by field redefinition of the underlying closed string field theory. Would it be okay to take a break? Would you guys like to take a little break for 5 minutes? Because now I'm about to get into something else, which is requires a little bit more attention again. So. Okay. Okay, so I hope everybody enjoyed a break. Okay, hopefully heads are a little clearer now, and we can. So now we have cubic vertex and we have propagator. So we can glue them together. We can compute Feynman diagrams. Okay. So simplest diagram we could compute is 4-string scattering. So for off-shell open string scattering in particular, so we're interested in off-shell amplitudes. Okay. So we're interested in reconstructing A04. Okay. In terms of connecting our cubic vertex and our propagator. So for definiteness, I will focus on the S-channel diagram. So what this means is, so if we're computing this 1, phi 1, phi 2, phi 3, and phi 4, okay. So this means that, so in the S channel, we have states phi 1 and phi 2, which are coupled to each other through a cubic vertex, okay? Okay. Okay, and here I'm just drawing kind of a picture of a sphere viewed from on top, okay? And these are the coordinate patches. And then we connect with a propagator tube to another sphere, which is a cubic vertex coupling phi 4 and phi 3. Okay. Okay, and these are the local coordinate patches. This is phi 1. Okay. Okay, phi 1. This is our propagator. This is our propagator tube. And, okay. And then, so this diagram will correspond to, in the usual z coordinate on the moduli space, okay. It corresponds to the limit where the phi 2 puncture approaches the phi 1 puncture at the origin. Okay? And there's phi 3 puncture here and phi 4 at infinity. So when this propagator is long, we know that this phi 2 puncture is going to be close to the phi 1 puncture. Okay? So when it's short, we don't really know. Okay, not yet. But at least this is what this diagram represents. So one might guess, okay, based on S and T channel duality of the 4-string scattering, that this diagram may actually contain the full string theory amplitude. Okay. So the factorization over the S channel is manifest, but perhaps maybe if this propagator is short enough, the T channel will also appear. Okay. But I'm just going to claim that, okay, we will see that this actually doesn't happen. So, so this diagram won't cover the whole plane, the whole moduli space. So, okay, so now we've just drawn a picture of the diagram we're computing, but it's not really clear. So this is some Riemann surface, which is divided into various coordinate systems, okay? And it's not really clear how these coordinate systems patch together into some global coordinate where you can actually compute correlation functions of these vertex operators, okay? So this is somehow the most challenging problem of closed string field theory, is that by gluing things together, you get surfaces that are not too hard to visualize, but then you have to apply some kind of uniformization and transform these pictures into coordinate systems where you actually know how to compute the correlation functions, okay? So in the case of the sphere, we need to transform this picture of the 4-punctured sphere into the complex plane, so into this picture, okay? So this can be done by following some steps, okay? So let me draw some pictures. So let's start with the cubic vertex, which is coupling phi 1 and phi 2 on the left here, okay? So in the complex plane, this cubic vertex is, okay, it's basically drawn here, but let me redraw it again. It's given by these bubbles, these circles, around 0 and 1, and another bubble around infinity. Okay. Okay. Inserted here. Phi 2. It's inserted here. Okay, so this is at 0 and 1. And then at infinity, we insert another state which corresponds to the propagator. Okay, so this is a representation of what that part of the diagram means. Okay, so now we're on the complex plane. Okay. Okay, good question, and I should have emphasized this. This calculation I'm going to do is only really possible for the SL2C vertex. It is possible on computer, maybe, with Witten vertex, but that is the reason. Okay, maybe later I could tell you exactly what goes wrong if you do the analogous thing with the Witten vertex. So now we start with this picture of this cubic vertex. And what we want to do, okay, the first step is we want to map this, okay, we want to map this propagator local coordinate patch into the unit disk. This can be accomplished by acting with, okay, by conformal transformation with F3 inverse. So this just maps this propagator region back into the local coordinate disk. And then you will find that the propagator is inserted at a unit disk around the origin. And the punctures of phi 1, phi 3 are out here. So we've just done a conformal transformation of the conventional picture. And now we have this propagator local coordinate patch is now just the unit disk. Okay. And then we do a further conformal transformation by something that's called, okay, Bpz Conformal Map, which is just an inversion. So we just take I of z goes to 1 over z. And this exchanges the unit disk inside here with the unit disk outside and sets the propagator puncture back out to infinity. And then we will have a picture that looks like this. Okay, so now we will have the unit disk. The propagator will be at infinity. Propagator punctures at infinity again. But now the coordinate patches of phi 1 and phi 2 are symmetrically located like this. Okay. Okay. And in particular, they're embedded in the unit disk. So as we've emphasized many times, you can naturally view the unit disk as a state in your state space. And this unit disk with phi 1 and phi 2 inserted here, this unit disk represents a state which is in some sense the product, a multiplication of phi 1 and phi 2. Okay? Okay, so now you're getting into some subtlety that that I wanted to hope nobody would notice, but now you ruined it. But you could still take this picture and you can do an SL2C or sorry, SL2R transformation of the unit disk. Okay? But this procedure that I followed gives you the correct representation. And the reason is because you want the unit disk like this, but you also want the unit disk with a particular parameterization of the coordinate around the. So unless you do something that's basically equivalent to this, you might get the unit disk, but you may have the wrong parameterization. Okay. So okay, maybe a. Okay, so now we have a product of the states phi 1 and phi 2 represented as a unit disk. And now we can act with the propagator. Okay? Okay. Okay, and this will give a picture, okay, where you still have the unit disk. Okay. But now the unit disk that we started with will be shrunk by the factor of e to the minus s and rotated by a factor of e to the I theta. Okay. And then this annulus here represents the propagator tube. Okay. Okay, so just to emphasize again, so okay, we did the conformal transformation of the cubic vertex, and we are left with here, and we ended here. So now what we're supposed to do is we're supposed to remove the region outside of this unit disk. So we're removing this coordinate patch, and then we're dealing just with this unit circle itself as a state. And if you apply the propagator to this, then you get this picture. Okay. Okay, but now we still have a unit disk. Okay. Still have a unit disk. And now what we can do is we can attach it to the cubic vertex, which is coupling phi 3 and phi 4. Okay. So now we look at the cubic vertex on this side of the diagram. In the usual representation, it takes the same shape as the picture I just erased. Okay, and okay, so now we have, so actually it's closer to here. Now we have the phi 3 puncture here and the phi 4 puncture at infinity. Okay, and what we will do is we will take this picture, this configuration on the unit disk, and we map it into here, into the coordinate patch around the origin, using F1. Okay? And if you do that, what you will find is a picture that looks like this. Okay, phi 4, or phi 2. And now, do I have another color or something? Just to emphasize. So now, okay, this blue is not very distinctive. Okay. So now I'm outlining in purple the regions of this plane, which actually represent local coordinate patches of states. So this little annulus in here is our propagator tube, okay? And in order to compute the S-channel diagram, we have to integrate over the length of the propagator and the twist angle, and this will basically be integrating over the size of this annulus, and we'll also be kind of rotating these little coordinate patches inside here. Okay. So, are there any questions? Okay. So, so we followed a number of conformal transformations, and now we have a representation of this diagram, of this S-channel diagram, on the complex plane. Okay, so on this surface has now been mapped into the complex plane like this. Yes, so in order to have total symmetry, you will need to include the T and U channel diagrams.
Any subsymmetry of a permutation over 4 points?
Yes, there's the exchange symmetry implied by the symmetry of the cubic vertex itself. So these two, so if you permute these two, or you permute these two, that's okay, but this permutation is not okay. Yes. Okay, so now we have, okay, a section of P hat 04, okay, in a portion of moduli space okay, near the S-channel degeneration. So we can ask, okay, so it's natural to ask whether this section actually in some sense defines a global section, okay, of P hat 04. So it's clear from this picture that it does not, because in order for this to be a global section, the position of the second puncture has to be able to wander around the whole complex plane, okay? But you see here that it's trapped inside the local coordinate patch of F1, okay? So this guy can never get too far away from phi 1, so this diagram, the S-channel diagram, will not cover the whole moduli space of this 4-point amplitude. So in this sense, okay, S and chi channel duality is lost. Yeah, so there's a little further modification which might be natural, which is to shift this guy up a little bit. So the phi 1 is at 0, and then, okay, this will also shift a little bit, but then you can just rotate it by normalizing that to 1. And okay, the true, okay, yeah, so let's, yes.
In order to see concretely what is the region of the space, states that you cover, you can fix one of the two punctures in 0, keep phi 3 in 1, and keep phi 4.
Yeah, so in fact, that's what you should do, but you can kind of see already that that's not going to change this picture a whole lot, because the phi 1 puncture is already going to be fairly close to 0. Yes. Yes. So, okay, so further, okay, I wanted to mention that we have a section of P04, okay, in the boundary of moduli space, and this parameter lambda equals e to the minus s plus I theta is a holomorphic coordinate on this section. Okay. So, so it's clear that if one following the sequence of conformal transformations, this coordinate on the moduli space only appears in this step where we put in the propagator tube. And in particular, nothing in this step depends on lambda bar. Okay? So this means that the section of P04 that we have constructed is in fact a holomorphic section in this corner of the moduli space.
And if you consider the other channel T, which is, for example, obtained by exchanging phi 2 and phi 5,
Yeah, so then you would also give a...
get a different moduli, and with this two region have probably an overlap. And the change of variable between the two lambda in S.
Yes, so let me finish saying what I wanted to say. So because this section of P04 is holomorphic, okay, even though this section is only defined in this corner of moduli space, we can try to construct a global section by analytic continuation, okay, of this section that we've defined here. And okay, but it's clear that this section will not be an admissible section. Okay, so the way you see that is that, okay, in this picture you see that, okay, these coordinate patches are changing as you change the moduli, right? As you change s, or as you change lambda. But the coordinate patch of phi 3 and phi 4 are obviously independent of lambda, okay? So that means they will remain independent of lambda upon analytic continuation. But you know that these local coordinate patches have to shrink if when the phi 2 puncture approaches phi 3, or when it approaches infinity. So you know that if you analytically continue this section, okay, outside the region where it's properly defined, then you will get local coordinate disks that are overlapping. So it's not an admissible section. So this, okay, just further goes to show that off-shell you really don't have duality between S and T channels, even through some analytic continuation. Okay, so globally.
It means that the transition function, either you have some singularity somewhere, or they are not complex, you have to go to the real element.
So this was a conjecture I gave to Ron Donaghy, that there is no holomorphic global section on PGN. But this is an example of okay, how that some motivation for that conjecture. Okay. Well, in this case, as I was saying, if you analytically continue the section, Okay, I'm not really sure how far it can be continued, whether it encounters branch cut or some wall of poles or something. Okay, actually, it shouldn't be too hard to check because we have the explicit formulas. But what I was saying was not necessarily that one would encounter a singularity in this section, but that, okay, even if one didn't, okay, you know that it can't be an admissible section because the shape of these, the shape of the phi 3, and phi 4 patches has to change as you approach the appropriate corners of moduli space to avoid the disks from overlapping.
So it's probably like you will be prevented from an analytic continuation after a certain.
Well, you would still have the analytic continuation. You would just find that your coordinate patches were being mapped on top of each other. Okay, so for a generic, okay, so for perturbative string states, you might still be able to compute the off-shell amplitude with that section, but for a non-perturbative string state, you would encounter singularity at some point when you tried to integrate over that section. Okay. So, so now we've explained in detail that the S-channel diagram does not cover everything, okay? But it's, of course, natural to include the contributions from the T and the U-channel diagrams, okay? And if you do that, you can look at what portion of the moduli space is covered, okay? So you have the portion around 0, which we said, which we've explained already, was covered by the S-channel. There's a portion around 1, which will be covered by the T-channel diagram. And there's a portion around infinity, which is covered by the U-channel diagram. Okay? Okay. So, in fact, the calculation of the T and U channel diagrams is essentially identical to what we've already done. You just have to relabel the states, and then, do the appropriate SL2C map of this region into this region. Okay. And this is what you will find. I actually didn't have time to do this calculation, okay, but I know that this is what the picture is supposed to look like, okay? Okay, it looks plausible. Okay, so I will leave it as an exercise. Yet another exercise for people who finished the last one to characterize or really I don't want you to just talk about it, I want you to compute it. Compute the missing region. Okay, so this is a rather remarkable simplification we have because we're using this SL2C vertex, that we can actually do a computation like this by hand. And if you're interested in closed string field theory, this is a good exercise to do because you can really do it and not just imagine it. I don't know. With the Witten vertex, they would touch. With this vertex, I don't know if they touch. It's probably, yeah, I don't know. So this region, which is the missing region on the moduli space, I will call pi dot v04, okay, for reasons to be explained in a moment. They should touch?
Well, at least two of them, yes, because if you take the distance of, for example, phi 2 equal between phi 1 both S and D channel.
What?
If you take a phi 2 at a equal distance, I would say that if you can move a phi 2 to a distance in between the phi 1 and phi 3,
Uh-huh.
this is both S and D channel. So they should overlap if it is possible to move F2, phi 2 at Z equal 1/2.
I don't know if it's possible. Okay, that's because I didn't do computation. Well, I hope somebody here will, maybe a student will like to check this. And there's also a possibility of some surprise, which would prove me wrong. But I won't talk about that because just to give you a little sense of mystery as to okay. But okay, so the point is, okay, so we have S, T, and U channels now all accounted for, but it still seems we have some missing portion of the moduli space. Okay, so the natural interpretation is that we need an elementary 4 vertex. So this elementary 4 vertex would be specified by a section of P04, okay, which we will call V04. And we integrate the measure along this section, okay. So we have some section of, some local section of P hat 04. Of P hat 04. Which is defined in this missing region. So in this missing region, we have to basically say, we have to make some choice of what these local coordinate maps should be, okay? And this choice is not determined by the cubic vertex in the propagator, but it's our choice to make, okay? And, okay, so we would also want, okay, so one condition is that, the technicality, okay, that V04 should be symmetric. A symmetric section, okay. Okay, this, just as with the cubic vertex, we impose the analogous condition, and that is again just to avoid having proliferating our sections. So in this way, we only have to consider one section, and if this section is defined over this region, okay, then we can integrate the measure to define a fundamental quartic vertex, which should appear in the closed string field theory action. Okay. So, okay. So, one thing. Okay. So, what I should mention is a comment from a while back, which is that an off-shell amplitude is almost the same as a vertex of the closed string field theory action, but with the boundaries of moduli space missing, okay? So this is the explicit realization of that. So if this V04 was in fact a global section of P04, then this would be the full off-shell 4-point amplitude. But instead, we've cut out some regions here towards the boundary of moduli space, okay? So another condition, okay, so this is one condition. Another condition on our choice of section V04 on this region is that, okay, V04 should patch together with the S, T, and U diagrams to define a continuous global section of P hat 04. So what that is saying is that as we cross from this region of the moduli space to this region, or this region to this region, as we cross these boundaries, the choice of local coordinate map shouldn't have some discontinuity. Okay, so the local coordinate maps should be continuous through the interfaces between these regions. Okay, and if it is continuous, that means that you will now have a continuous global section of P hat 04, and your off-shell amplitude, the off-shell 4-point amplitude, will be BRST invariant. Yes. What? Yes. Can you analytically continue a continuous function, or what do you mean? So you can analytically continue these patches, and as I said, you can only analytically continue these sections so far because you know that there's going to be problems at some point.
About this, there is a further condition you should probably impose, is that when the external states are physical, the analytic continuation of whichever patch should be equal to what you get from V04. Because when the external states are analytic, are physical.
So elements of this HQ that I was referring to?
Yes.
So if it's an element of HQ, then all of these choices will drop out.
Yes.
So the choice of section will evaporate.
Yes.
So even the section could be discontinuous, I think, in that case.
Well, okay, but
Because that data doesn't appear with the vertex operator, the choice of local coordinates.
to V04 when you patch with
On-shell states?
yes.
You will just get 4-point function of on-shell vertex operators. Okay. And okay, you will get basically the on-shell 4-point amplitude, but with a yes, with a restricted region of integration, that the vertex operator will now only appear inside here. Okay.
But this should be exactly equal to a dynamic continuation of S channel also.
Yes, so this will also be automatic. So this will be automatic because okay, the data about the local coordinates drops out. So all you have to do is you make sure that the puncture is covering everything in here from the quartic vertex, and it's covering everything in here from the ST and U channel diagrams. And basically, we're proving already that these diagrams cover everything, that the puncture goes everywhere if you include ST, U channel, and a fundamental quartic vertex. By definition or by construction, we've made sure that the puncture wanders everywhere. Okay? So that means that if we are lucky and we are just dealing with BRST invariant conformal vertex operators, then actually the data that we're talking about, the local coordinates and stuff, will just drop out, and then you're guaranteed that we have the correct on-shell 4-point amplitude. Say that again?
If you consider the parameter for which you can get all the disk to touch,
Uh-huh.
the 3-point vertex will have an overlap in the patch sheet.
So you know this for a fact, or you just calculated this?
I have the figure, I draw the figure, so it's...
Okay. Okay, that's quick. Okay, thank you. Okay, so for the vertex that I defined, you have some space in here. Okay. For the Witten vertex, I happen to know, as a matter of fact, that you don't have space in here. Yes. But I think that calculation is not so easy to do by hand. I'm not actually sure how it was done. But
That's all the information on the section dropout, because the lambda is cannot drop out.
lambda?
Lambda is the coordinate of the section, it cannot be drop out
Lambda is a coordinate on the moduli space. And it also defines a coordinate on the section because, yeah. So we have. So, okay. So, what else?
Okay, so now you have characterized the missing region.
Uh-huh.
Can you build now explicitly this corporate vectors?
Yeah, so now, okay, subject to these two conditions, you can choose the 4-point vertex at your pleasure, okay? So imposing symmetry is a little bit annoying. It gets more annoying with more vertices, but okay, it can be done. Or with a higher point vertex, it gets more and more annoying, but it can be done. And, okay. Right, so the physically important condition is that this should patch together to give a continuous global section. All these diagrams should patch together to give a continuous global section of p hat 04. So, okay, so actually it's interesting to be a little bit more formal about this condition too. Okay, so it can be formulated as a part of a hierarchy of conditions. On the sections VGN defining closed SFT vertices. So let me write a few of these conditions. Okay. First condition is just that the boundary operator squares to 0. Okay, it's not really a condition. Second condition is that the boundary of V03, the section that defines our cubic vertex, is 0. So this is clear because V03, the base manifold in this case is just a point, and if you take the boundary of a point, you get nothing. Okay. Then there's another condition on V04, okay, which can be written in this way. In some sense, it's a boundary of the moduli space of the three-punctured sphere. Okay, but the moduli space is zero-dimensional, right? So it vanishes.
CO3 is actually the boundary of a moduli space associated to the CO3 vertex.
So the moduli space is a point.
Yes.
V0, and on this point, you can define a fiber bundle, which is p hat 03, okay? This fiber bundle consists entirely of one fiber. V03 is a point in this fiber, okay? And, okay, subject to maybe some symmetry condition, okay?
But V03 is not the state, but you are indicating the point on P hat 03.
Right, okay, that was the confusion. So, in fact, that confusion was part of motivation for my notation, right? So that this state is, in fact, this is just emphasizing that this vertex is entirely characterized by this choice of local section, okay? So that is why I wrote, so this is not the same as the vertex. The string field theory vertex. This is a geometrical space, okay? And then there's this condition on the boundary of V04, and then there are an infinite hierarchy of higher conditions. So let me explain this. So this is a section of P04, which is defined on the interface between these two regions. And this section is defined by gluing your cubic vertices, possibly with some twist angle, okay? So you just glue the cubic vertices without inserting a propagator tube. You just glue them and maybe you twist them, okay? And this will define for you some section of P04 defined on these boundary regions. And this equation is just saying that the boundary of V04 should match what you get here. So this is basically a continuity condition on your choice of global section.
Should I interpret those conditions as a kind of topological assertion, or it is actually something more about the transition function?
This is just a way of saying things that is nice, as far as I can tell. So this in these equations is not contained anything more than the claim that you need a continuous global section of PGN, okay? But, that you should choose your vertices so that this is the case, okay? And if you choose your vertices, then they will satisfy a hierarchy of equations that look like this, okay? And these equations are called the geometrical BV equations, or equation, depending on how tightly you want to package it. So these equations are actually a statement of the principle of nonlinear BRST invariance, which is the symmetry principle which determines the form of closed string field theory. Okay, so this, as we were saying at the very beginning, the notion that you have a nonlinear object that's squaring to zero is really what determines the form of the theory. And this is the imprint of that statement at the geometrical level in terms of the sections of this fiber bundle over the moduli space. Okay. Okay, this condition is also, related, or it's implied by the fact that you have a consistent gauge-fixed path integral for closed string field theory, okay, which in particular means that you have a solution of the quantum Bartolin-Vilkovisky master equation. So the master equation essentially implies these conditions. Okay, so now, okay, so as you might imagine, so now we have propagator, we have cubic vertex, we have quartic vertex, and now we have to proceed computing Feynman diagrams, including both cubic and quartic vertices. And if you go to the next higher order, so for example, compute a 5-point amplitude on the sphere, it's not surprising that you will also find that you need a fundamental 5-point vertex to fill in the missing regions of the moduli space. Okay, so in this way, it's clear that that you will need. It's not clear, but the expectation is that you will need an infinite number of vertices in the closed string field theory action. And these vertices we can write as VGN, which are given by integrals over local sections VGN of BGN, V hat GN, of the measure. Okay? And these regions, these local sections, will have to satisfy this geometrical BV equation in order to have consistent amplitudes. Okay? So that means that we basically know, based on all of this analysis, that the closed string field theory action will take the following form. Okay. So this is kind of analogous to the equation that I was writing at the beginning. So we will have, for example, a one-loop tadpole vertex, and etc. So this is analogous to the expression I was writing at the beginning. And so you have all this infinite sequence of vertices, and then you basically know that they derive from an action principle, which is non-polynomial and has an infinite number of counter terms at the quantum level. Okay, so one thing that I didn't describe yet is the quadratic term in the action. So the quadratic term in the action is, okay, it's basically what fixes the form of the propagator, but of course it doesn't appear as an elementary vertex in itself, right? So even though we know these things, or at least we know them in principle, okay, we have to say something about this. So unfortunately now I have run out of notes, so I really don't know what to say, but okay, I can. So this is also something that is usually said at the beginning of a lecture on closed string field theory, not at the very end, because it's actually the easiest part, so people want to explain to you something that's easy because it makes you feel good, so they do it the first thing. But okay. It's not, I'm not saying it's trivial. It was quite non-trivial finding the correct kinetic term, but it's not very technical to describe. So let me say, what, so the question is, what is V02? Okay, so V02, okay, so first ingredient we need to define V02 is the Bpz inner product. So this is a map from H tensor 2 into H tensor 0. And often it's written that Bpz acting on phi 1 tensor phi 2 is often written as phi 1 phi 2. And the definition of the Bpz inner product is in some sense obvious. So we saw that a state can be defined by a unit circle with some vertex operator. Okay, so this is a state, but the complement of the unit circle in the complex plane is empty. Okay, but if you want to, if you want to turn this state into a dual state, then it's natural to act by the inversion map. Okay? And this will, okay, exchange the unit disk to its complement in the complex plane. Okay? And now with the complement, now if you have a surface which is the complement of the unit disk, it's easy to contract with the state because you just take the disk of the state and you patch it in there. Okay? So this conformal map, okay, is the thing that defines the Bpz inner product. And it's just given by inserting, okay, phi 1 at 0 and taking the inversion map of phi 2 at 0 and computing this correlator on the complex plane. Okay? So this defines the Bpz inner product. Okay, maybe I shouldn't. So the other thing we need is the symplectic form. Okay, this is something I mentioned at the beginning. This is given by minus, I think it's a minus, Bpz, and then 1 tensor C naught minus, okay, where C naught minus equals a half C naught minus C naught bar. Okay, and it has the useful property that it commutes with B naught minus to give 1. So this symplectic form will actually be, okay. Yes, okay, so graded commutator. It's actually defined on level match states, or states that satisfy level matching and B0 minus constraints. Okay, so this symplectic form, you need this C0 minus in here, because otherwise the symplectic form acting on any pair of states satisfying B0 minus condition will vanish. Okay, so you need the C0 minus in here to prevent this symplectic form from being degenerate. And then it turns out that V02 is just given by the symplectic form times 1 tensor q up to a possible sign. Okay. So you get the BRST operator appearing in the kinetic term. No, I'm not explicitly symmetrizing them. If I had had more time, I would have gotten into the symmetrized tensor algebra description of the coalgebra formulation of L infinity, which requires the symmetrized tensor algebra. But yeah, so if you act a symmetric map on a non-symmetrized state, of course, it's the same as acting a symmetric map on a symmetrized state. So we don't have to use that formalism a priori. Okay, and in fact, it's kind of inconvenient in the context of the symplectic form, because the symplectic form is antisymmetric. So if it acts on a symmetrized state, it just gives 0. So in this sense, it's more convenient to use. Okay. Anyway, so I guess that's it. Okay, I could have given a better presentation of the kinetic term here, but I think okay, this is enough for now. Okay, thank you.